uniform circular motion. So pretty easy to explain. When you have uniform circular motion, you have an object that is moving around in a circle. And that object will always have, if it's uniform circular motion, a velocity vector that is tangent to the center of the circle. So if I mark the circle, well, it's not quite the center, but it's pretty close. If you mark the center of the circle and you bring a radial line out, it will touch a point, and the velocity of the particle will always be at a right angle to that point. So to define uniform circular motion, it is moving in a circular path with constant speed. Not constant velocity, but constant speed. We're going to define that velocity and just say, well, we're going to define that speed just as v. And the radius of the circle will just be r. All right, now I drew that particle in that position for a reason. I want to do a second location for the particle. After it has moved for some amount of time, it will move over to a position here, symmetric on the opposite side, still a distance r away, and there will be an angle delta theta between those two positions. This will result in a delta r, a change in position or a displacement right through here. And the reason why I wanted to do it that way is we get velocity vector going up and diagonal, and velocity vector coming down and diagonal for the initial and the final, leading to, and I really should make this bigger even though it doesn't match the size of the vectors. So I will do that. Make the vectors a little bit too big. That was our initial, this is our final, and that is delta v. Now we want to know what is the angle inside here. So to explain that, if this is at an angle theta, well, how do I want to describe it? Yeah, sure, that'll work fine. If this is an angle theta 1 coming out along here, coming out along the horizontal, this is also theta 1. That is 90 degrees. So this is v at an angle of theta 1 plus 90 degrees. If we look at the final case, we're now at this angle all the way over here. I'm going to change colors. How about blue? That'd be our theta 2. If we drag this out, get the horizontal, this is also theta 2. That is 90 degrees. So this one would be v at theta 2 plus 90 degrees. Okay, if we take the angle that each one of these is at and we do the difference between them, then the angle that it will have changed and the angle inside here would basically be, well, that's the initial, that's the final, so final minus initial will give theta 2 plus 90 degrees, minus theta 1 plus 90 degrees, and we see that that is also delta theta. Well, we know two sides are equal and we know the angle in between is the same. So we actually know that they share a strong relationship. This is an isosceles triangle because the sides are the same in both cases, for the physical triangle with r and delta r, as well as for this triangle with v and delta v. So that means we have similar triangles, which means delta v over v is equal to delta r over one of the r's. And the reason we want to use this is we want to find the acceleration. So delta v gives the direction. I'm just going to type the rest of this. Delta v gives the direction of the acceleration. And here you can see it points, the mean position would point directly towards the center. And as we bring them closer together, it stays pointing directly towards the center. And if you choose any pair of points around the circle, you'll always find that the acceleration vector would point towards the center of the circle. So we have a centripetal acceleration, an acceleration that points towards the center. Oops. I'll change the color to be more readable there. What about the size? Well, acceleration is defined as the change in velocity over the elapsed time. So in this case, we can use the similar triangle relationship to rewrite delta v. Delta v would be equal to v times delta r over r. So we'd have v over r delta over delta t. If we let the time become very short, the 2 points will get very close together, and delta r over delta t will just become the same thing as the velocity all over again. So we end up with the acceleration looking like v squared over r, pointing towards the center. Okay. So the centripetal acceleration is equal to v squared over r. We're actually going to make a fair amount of use of that because that is true universally of uniform circular motion. But it's also true even for non-uniform circular motion, which we'll talk about in just a moment here. All right, for uniform circular motion, since the speed is constant, we can find the time to complete a circle pretty easily. So v is equal to distance over time. Rearranging that, time is equal to distance over speed. The distance is 2 pi r. And we would divide by the speed. Okay, so that is the period for revolution. Okay, there's another thing I want to define while we're at it. That is the angular speed. Angular speed is omega, and it is found by taking the number of radians to go a full circle and dividing by the period. If we take the period that we've just found, we'll find that omega is 2 pi divided by 2 pi r over v, so we'll invert and multiply. And omega is equal to the speed divided by r. This gives us the second way of writing the centripetal acceleration. We can just say the centripetal acceleration would be omega squared times r, because that would be v squared over r squared times r. So second way of writing centripetal acceleration, but there is r first. Okay. I think that's pretty much everything we need for uniform circular motion. And let's talk about non-uniform circular motion for a moment. I'm thinking I probably should have split this video into two. But this will only take a couple minutes. Wait, where do you... Oh, there, fixed. All right. And non-uniform circular motion is what happens when your speed changes as you follow a circular path. Okay, that means our acceleration has both a centripetal And I'm thinking circumferential, but I know that's not the right one. Radial and tangential. So radial / centripetal will tell you about the force needed to keep it going in the circle. And tangential acceleration tells you about how the speed is changing as you go around the circle. So let's pull up another circular path. We'll mark a particle somewhere on it. That particle has a velocity, and then it has two different things going on. There will be a centripetal acceleration, and then let's say for the sake of argument that this is accelerating, in which case it will also have a tangential acceleration. And that leads to a net acceleration, an acceleration vector that has both tangential and centripetal components. And here's the important thing: the centripetal and tangential components are perpendicular to each other. So we know the magnitude of this vector A will be the square root of the centripetal acceleration squared plus the tangential. And yes, we can find the angle inside there if we want. We can look at the inverse tangent of the tangential over the centripetal component. All right, last thing I want to mention, our textbook has sort of a weird definition. It says the radial acceleration is the negative of the centripetal. The reason why is actually logical. A radial acceleration will be positive when it's outward and negative inward. Centripetal acceleration is positive when it's inward. So that's the real reason why we get the minus sign showing up. We'll have an example problem talking about this in class. For now, I think that's it for circular motion, so I'm going to stop the video there. I apologize it ran this long. I should have split it in two. It would have been 9 minutes and 5 minutes. And pardon for the cough.